Every photon of light reaching our telescopes carries information encoded during its journey across space and time. Some of these particles traveled for over 13 billion years, passing through cosmic events we can barely imagine. The James Webb Space Telescope now captures light from galaxies that formed when the universe was only 400 million years old, revealing mature spiral structures that challenge our models of early cosmic evolution. In 2025, we've learned to read these messages with unprecedented precision, decoding the chemical composition of distant stars and detecting frozen water in young planetary systems. Yet Webb's unexpected discovery of fully formed galaxies existing far earlier than predicted demonstrates how each answer reveals new complexities. Our expanding knowledge shows that the universe operates according to principles that required centuries of careful observation to understand. The foundation of modern space knowledge. The telescope transformed these ancient observations into precise scientific measurements. When Galileo turned his simple refracting instrument toward the heavens in 1609, he discovered mountains on the moon, 4 moons orbiting Jupiter, and countless stars invisible to the naked eye. His observations shattered the ancient model of perfect celestial spheres and provided crucial evidence for the heliocentric solar system. Within decades, astronomers across Europe were building larger and more sophisticated telescopes, each improvement revealing previously unknown celestial objects and phenomena. Newton's reflecting telescope design solved the chromatic aberration problems that plagued early refracting instruments. By using mirrors instead of lenses, astronomers could build much larger telescopes with superior image quality. The 100-inch Hooker telescope at Mount Wilson represented the pinnacle of this technology in the early 20th century. Edwin Hubble used this instrument to make the revolutionary discovery that spiral nebulae were actually distant galaxies, fundamentally expanding our understanding of cosmic scale and revealing that the universe itself was expanding. Photography revolutionized astronomical data collection by allowing astronomers to record permanent images of celestial objects. Photographic plates could accumulate light over hours or days, revealing faint stars and nebulae invisible to the human eye during direct observation. Astronomers could now measure stellar positions with unprecedented precision and track changes in brightness over time. The combination of photography with spectroscopy enabled detailed analysis of stellar composition and motion, marking the transition from purely visual astronomy to quantitative measurement. Space-based observatories eliminated atmospheric interference and enabled observations across the entire electromagnetic spectrum. The Hubble Space Telescope produced images of unprecedented clarity and discovered phenomena that ground-based telescopes could never detect. Hubble's observations revealed the accelerating expansion of the universe through distant supernovae measurements and provided evidence for dark energy. The Spitzer Space Telescope mapped infrared radiation from distant galaxies and revealed the structure of cosmic dust clouds, while also contributing to the discovery of the 7-planet TRAPPIST, one system located 40 light-years away. Modern telescopes generate enormous quantities of data that overwhelm traditional analysis methods. A single night of observation can produce terabytes of information requiring sophisticated computer processing. Digital detectors replaced photographic plates, providing instant electronic readouts with much higher sensitivity. Charge-coupled devices and other electronic sensors can detect individual photons and measure their wavelengths with extreme precision. Automated systems now control telescope pointing, data collection, and initial processing without human intervention. Machine learning algorithms analyze astronomical datasets at speeds impossible for human researchers. Pattern recognition software identifies new astronomical objects from survey data containing millions of sources. Neural networks classify galaxies, stars, and other celestial phenomena with accuracy that exceeds human observers. Computer algorithms automatically detect transient events like supernovae and variable stars from continuous monitoring programs. The combination of advanced detectors and artificial intelligence has accelerated the pace of astronomical discovery exponentially. International collaboration has become essential for modern astronomical research. Major observatories operate as shared facilities, serving researchers from multiple countries. The European Southern Observatory coordinates telescopes across Chile for astronomers throughout Europe. The Atacama Large Millimeter Array combines signals from 66 radio antennas to create a virtual telescope with unprecedented resolution. Global networks of observatories coordinate observations of time-sensitive phenomena like gamma-ray bursts and gravitational wave events. Amateur astronomers contribute meaningful data to professional research through citizen science projects. The Galaxy Zoo project enlisted volunteers to classify galaxy shapes from Hubble Space Telescope images. Amateur observers discovered numerous exoplanets by analyzing light curves from professional survey missions. Dedicated amateur astronomers monitor variable stars and track asteroid movements with equipment that rivals professional facilities from previous decades. Social media and internet collaboration enable rapid communication of new discoveries between professional and amateur astronomers worldwide. Robotic telescopes operate continuously without human supervision, maximizing observation efficiency. Automated survey programs monitor the entire sky for changes and new objects. Machine learning systems prioritize interesting targets for follow-up observations. Remote operation capabilities allow astronomers to control telescopes from anywhere in the world. Robotic systems can respond to alerts within minutes, capturing data from transient events that would otherwise be missed. Spectroscopy reveals the chemical composition, temperature, density, and motion of celestial objects through analysis of their light. Modern spectrographs can detect hundreds of chemical elements in distant stars and galaxies. Doppler shift measurements reveal the radial velocities of stars and gas clouds with precision of meters per second. High-resolution spectroscopy can detect the gravitational effects of unseen companions orbiting nearby stars. The combination of imaging and spectroscopy provides a complete physical description of astronomical objects. Adaptive optics systems compensate for atmospheric turbulence in real time, producing images from ground-based telescopes that rival space telescope quality. Laser-guide stars create artificial reference points for measuring atmospheric distortions. Deformable mirrors adjust hundreds of times per second to correct for atmospheric effects. These technologies enable ground-based telescopes to achieve theoretical resolution limits despite atmospheric interference. Multi-messenger astronomy combines observations of electromagnetic radiation, gravitational waves, and particle detection to study cosmic events. The detection of gravitational waves from merging black holes opened an entirely new window for cosmic observation. Neutrino detectors bury deep underground capture particles from stellar explosions and active galactic nuclei. The correlation of different types of signals provides unprecedented insights into the most violent processes in the universe. Our current understanding represents 4 centuries of technological advancement building upon ancient observational traditions. Each new instrument and detection method has revealed unexpected phenomena while raising new questions about cosmic processes. The exponential growth in data collection and processing capability has transformed astronomy from a descriptive science into a precision measurement discipline. Yet even our most sophisticated ground-based and orbital telescopes pale in comparison to the revolutionary capabilities now operating in the depths of space. The James Webb revolution continues. The James Webb Space Telescope has fundamentally altered our understanding of cosmic evolution through observations that consistently challenge theoretical predictions. Webb's infrared sensors have captured galaxies that existed when the universe was merely 400 million years old, appearing as they were when cosmic time had barely begun. These ancient systems show unexpected maturity and organization that challenges fundamental assumptions about early cosmic evolution. The telescope has identified fully formed spiral structures in galaxies that theoretically should still be chaotic clouds of gas and dust. Massive central bulges appear in these early systems decades before computer models predicted their formation. The spectroscopic data reveals heavy elements like carbon and oxygen in concentrations that suggest multiple generations of stellar evolution had already occurred. These observations indicate that galaxy formation proceeded at breakneck speed during the universe's infancy, compressing billions of years of expected development into a few 100 million years. The telescope's infrared vision penetrates dust clouds that completely obscure visible light, revealing stellar nurseries in unprecedented detail. These observations show brown dwarf formation occurring alongside typical star formation in dense molecular clouds. Webb detects the heat signatures of protostars still accumulating material from their surrounding disks. The infrared data reveals how magnetic fields channel gas flows during the earliest stages of stellar birth. Temperature measurements show the precise conditions needed for different types of stars to ignite nuclear fusion. The telescope captures the moment when stellar winds begin clearing away natal dust cocoons. These detailed observations track the complete life cycle from collapsing gas cloud to active main sequence star. Atmospheric analysis of potentially habitable exoplanets has reached extraordinary precision through Webb's spectroscopic capabilities. The telescope can identify individual molecular species in exoplanet atmospheres by analyzing how starlight filters through these distant worlds during planetary transits. Water vapor signatures appear in the atmospheres of several rocky planets orbiting within their star's habitable zone. Carbon dioxide concentrations provide clues about greenhouse warming and atmospheric pressure. Methane detection remains particularly significant because biological processes represent the most likely source for this molecule's persistence in rocky planet atmospheres. The telescope has identified complex atmospheric chemistry on worlds orbiting red dwarf stars, previously considered poor candidates for habitability due to stellar activity. Supermassive black holes with masses exceeding 1 billion solar masses have been detected in galaxies formed less than 700 million years after the Big Bang. These discoveries contradict existing models that require hundreds of millions of additional years for black holes to reach such enormous sizes. The accretion rates necessary to grow these black holes so quickly approach theoretical maximum limits. Webb's observations show these early supermassive black holes actively feeding on surrounding gas, while simultaneously triggering intense star formation in their host galaxies. The relationship between black hole mass and galaxy properties appears fully established in these early systems. Some of these ancient black holes outweigh their entire host galaxy, suggesting formation mechanisms completely different from those operating in the modern universe. Precision measurements of distant supernovae and Cepheid variable stars contribute new data points to the ongoing Hubble constant controversy. Webb's infrared observations reduce measurement uncertainties caused by interstellar dust extinction. The telescope's superior resolution separates individual stars in distant galaxies that appear as single points of light to other instruments. These measurements consistently support expansion rates that conflict with predictions based on cosmic microwave background observations. The discrepancy suggests either systematic errors in measurement techniques or fundamental gaps in our understanding of cosmic evolution. Webb's data indicates the universe may be expanding 8 to 10% faster than cosmological models predict. Brown dwarfs and rogue planets represent a substantial hidden population of substellar objects throughout the galaxy. Webb detects these failed stars through their thermal infrared emission, revealing objects too cool and dim for previous telescopes to observe. The telescope has identified brown dwarfs with surface temperatures below 500 degrees Celsius, approaching the boundary between stars and planets. Free-floating planetary mass objects appear scattered throughout star-forming regions, apparently ejected from their original planetary systems during gravitational interactions. Webb spectroscopy reveals complex atmospheric chemistry in brown dwarfs, including cloud formation and weather patterns similar to gas giant planets. Complex organic molecules, including polycyclic aromatic hydrocarbons, appear throughout star-forming regions in distant galaxies. Webb spectroscopy identifies these carbon-based compounds in environments with temperatures and radiation levels previously thought too extreme for molecular survival. The telescope detects methanol, formaldehyde, and other organic species in molecular clouds located thousands of light years from Earth. These discoveries suggest that organic chemistry operates on galactic scales, potentially seeding planets throughout the universe with prebiotic materials. The infrared signatures reveal organic molecules embedded in ice grains surrounding young stars. The most distant galaxies observed by Webb show redshift exceeding Z equals 13, corresponding to observation times when the universe was less than 400 million years old. These remote systems challenge the theoretical framework describing early cosmic evolution. The galaxies appear surprisingly large and massive for their cosmic age. Star formation rates in these early systems exceed those found in modern galaxies by factors of 10 or more. The stellar populations show evidence for rapid chemical enrichment through multiple generations of massive stars. Theoretical predictions consistently underestimated both the formation speed and final masses of early galactic systems. Webb observations show that galaxy assembly occurred through rapid mergers and accretion events rather than gradual growth processes. The first billion years of cosmic history witnessed more dramatic evolution than the subsequent 13 billion years combined. These discoveries require fundamental revisions to our understanding of how structure formation proceeded during the universe's youth. Webb's revelations about planetary atmospheres and the widespread distribution of organic materials have expanded our perspective on where life might emerge, while systematic surveys continue identifying new worlds at an unprecedented pace. The exoplanet census explosion. The NASA Exoplanet Archive crossed the 5,630 confirmed exoplanet threshold in 2024, marking humanity's transition from wondering whether planets exist around other stars to cataloging their incredible diversity. This milestone represents more than simple numbers in a database. Each confirmed world required years of careful observation and analysis to verify its existence. The exponential growth in discoveries over the past decade reflects revolutionary improvements in detection sensitivity and data processing capabilities. 25 years ago, astronomers knew of fewer than 10 exoplanets. Today's catalog reveals that planetary systems represent the normal outcome of star formation rather than rare cosmic accidents. Statistical analysis of confirmed discoveries suggests that every star in our galaxy hosts at least one planet on average. The 5,000-plus worlds span an enormous range of sizes, compositions, and orbital configurations that defies easy categorization. Ultra-hot Jupiters orbit their parent stars in less than 4 days, experiencing surface temperatures exceeding 2,000 degrees Celsius. These bloated gas giants have atmospheric temperatures hot enough to vaporize metals like iron and titanium. Tidal forces from their nearby stars distort these planets into egg shapes while stripping away atmospheric material. At the opposite extreme, super-Earths orbiting in the habitable zones of red dwarf stars maintain surface temperatures compatible with liquid water. The Transiting Exoplanet Survey satellite systematically monitors 200,000 nearby stars for planetary transits. TESS divides the sky into sectors that receive 27 days of continuous photometric monitoring. The mission covers the entire celestial sphere over its 2-year primary mission duration. TESS achieves photometric precision sufficient to detect Earth-sized planets around Sun-like stars. The satellite's 4 wide-field cameras simultaneously observe 24-degree by 24-degree patches of sky. Ground-based follow-up observations confirm TESS planet candidates and measure their masses through radial velocity techniques. Transit photometry detects exoplanets by measuring tiny decreases in stellar brightness when planets pass between their star and Earth. Modern photometers can detect brightness changes smaller than 1 part in 10,000. The precise timing of these transit events reveals orbital periods ranging from hours to decades. Multiple transits allow astronomers to determine planetary size, orbital distance, and atmospheric properties. Machine learning algorithms now automatically identify planetary transit signals from continuous monitoring data streams. Radial velocity measurements detect the gravitational wobble that orbiting planets induce in their parent stars. Spectrographs measure Doppler shifts in stellar absorption lines with precision approaching 1 meter per second. This technique reveals planetary masses and orbital eccentricities that transit observations cannot determine. The combination of transit and radial velocity data provides complete physical descriptions of exoplanet systems. Advanced spectrographs use laser frequency combs to calibrate wavelength measurements with unprecedented accuracy. Mini-Neptunes represent the most common type of exoplanet despite having no analog in our solar system. These worlds contain between 2 and 4 times Earth's radius, while possessing substantial hydrogen-helium atmospheres. Their bulk densities indicate compositions intermediate between rocky terrestrial planets and gas giant planets. Mini-Neptunes probably formed as rocky cores that subsequently accreted thick atmospheric envelopes. The prevalence of mini-Neptunes suggests that planetary system formation commonly produces intermediate-sized worlds through processes that did not occur in our own solar system. Atmospheric characterization reveals the chemical composition and physical structure of exoplanet atmospheres through spectroscopic analysis. Water vapor, carbon dioxide, and methane signatures appear in transit transmission spectra of numerous hot Jupiters. Temperature profiles show the vertical structure of planetary atmospheres from cloud tops to deep atmospheric layers. Biosignature gases like oxygen and ozone could indicate biological activity on rocky planets in habitable zones. Simultaneous detection of oxygen and water vapor would provide strong evidence for life on distant worlds. Potentially habitable exoplanets must satisfy multiple criteria beyond simple location within the habitable zone. Atmospheric retention requires sufficient planetary mass to prevent atmospheric escape to space. Magnetic field generation protects planetary atmospheres from erosion by stellar wind particles. The host star's activity level affects atmospheric chemistry through ultraviolet radiation and particle bombardment. Recent discoveries show that subsurface oceans might exist on planets throughout the galaxy, expanding the definition of habitability beyond surface conditions. Circumbinary planets orbit both stars in binary star systems, experiencing complex gravitational forces from their dual stellar parents. These worlds challenge planetary formation theories that assume single-star environments. The changing stellar illumination creates extreme seasonal variations as planets orbit around both stars. Binary star systems comprise roughly half of all stellar systems in the galaxy. The existence of stable planetary orbits around binary stars significantly increases the number of potential planetary sites throughout the galaxy. Free-floating planets drift through interstellar space after ejection from their original planetary systems during gravitational encounters. These rogue worlds outnumber stars in our galaxy, according to gravitational microlensing surveys. Most rogue planets probably formed in normal planetary systems before ejection during close encounters with other planets or passing stars. Some may retain substantial atmospheres that could maintain subsurface liquid water through radioactive decay heating. The diversity of discovered worlds far exceeds theoretical predictions based on solar system architecture. Planetary formation appears to be a robust process that operates under a wide range of stellar and environmental conditions throughout the galaxy. While astronomers catalog thousands of distant worlds, robotic explorers continue investigating planets within our own solar system, searching for signs of past or present life much closer to home. Mars exploration reaches new heights. The Red Planet has become humanity's most intensively studied world beyond Earth, with multiple robotic missions operating simultaneously across its surface and from orbit. Perseverance has collected 24 rock and soil samples from Jezero crater, with several containing mineral formations that could preserve evidence of ancient microbial life. The rover's drilling operations target sedimentary rocks formed in aqueous environments billions of years ago. These samples show signs of carbonate precipitation and silica, deposits that form through water-rock interactions. The collected materials include fine-grained mudstones that accumulated in quiet lake environments where microorganisms could have thrived. Organic carbon signatures appear in multiple samples, though their biological or geological origin remains under investigation. The samples are sealed in titanium tubes and cached on the Martian surface for eventual return to Earth through future sample return missions. Laboratory analysis on Earth will provide definitive answers about potential biosignatures that current rover instruments cannot resolve. Ingenuity completed 72 flights during its extended mission, far exceeding its original 5-flight demonstration plan. The helicopter's aerial reconnaissance identifies optimal driving routes for Perseverance while avoiding hazardous terrain features. Flight operations revealed geological formations invisible from ground level, including layered rock outcrops and ancient shoreline deposits. The helicopter's camera systems capture high-resolution images of scientifically interesting targets before the rover arrives. Ingenuity's flights demonstrated powered flight capabilities in atmospheric densities less than 1% of Earth's. The helicopter survived multiple Martian winters despite design specification for a 30-day mission duration. Its success has influenced designs for future aerial vehicles, including larger helicopters capable of carrying scientific instruments. Laboratory analysis of Perseverance samples reveals detailed information about Mars' ancient climate through mineral composition and textural features. Phyllosilicate clay minerals indicate prolonged water-rock interactions under neutral pH conditions. The presence of olivine and pyroxene suggests rapid burial that preserved these water-sensitive minerals from alteration. Calcium sulfate veins cutting through bedrock record multiple episodes of groundwater flow. Isotopic ratios in carbonate minerals reflect atmospheric composition during their formation. The grain-size distribution in sedimentary rocks indicates flowing water velocities and transport distances. Rounded pebbles and cobbles provide evidence for sustained river flow over extended periods. Chemical weathering patterns show seasonal wet-dry cycles that could create habitable microenvironments. Ground-penetrating radar data from the Mars Reconnaissance Orbiter identifies extensive subsurface water ice deposits extending to depths of several hundred meters. These ice-rich layers contain more water than the Great Lakes combined. Some deposits lie within 2 meters of the surface, making them extractable with simple excavation equipment. The ice purity varies from location to location, with some deposits containing minimal dust contamination. Seasonal temperature cycles cause sublimation and redeposition of surface ice layers. The distribution pattern suggests that ice accumulated during different climatic periods over millions of years. These water resources could support human exploration and serve as rocket fuel for return missions to Earth. Methane concentrations in Mars' atmosphere show seasonal variations that correlate with surface temperature changes and potentially subsurface activity. Background methane levels remain near detection limits, but localized plumes contain concentrations up to 45 parts per billion. The seasonal pattern peaks during late northern summer when subsurface temperatures reach maximum values. Methane sources could include serpentinization reactions between water and olivine-rich rocks that produce hydrogen and methane. Alternatively, methanogenic microorganisms in subsurface environments might generate methane through biological processes. The gas appears to have a short atmospheric lifetime, suggesting active destruction mechanisms or localized sources. The correlation between methane emissions and geological features suggests possible connections to subsurface water systems. Organic compound detections by Perseverance's sample analysis at Mars instrument include complex carbon-bearing molecules in multiple rock types. Thiophenes, benzothiophenes, and other sulfur-bearing organics appear in mudstone samples from the crater floor. These compounds could form through biological processes or abiotic synthesis during hydrothermal activity. The diversity of organic molecules suggests multiple formation pathways or preservation mechanisms. Seasonal variations in atmospheric organic compounds detected by the Curiosity rover indicate ongoing sources or release mechanisms. The detection of organics in ancient lake deposits strengthens arguments for past habitability. The molecular complexity rivals that found in meteorites and suggests sophisticated carbon chemistry operated on ancient Mars. Delta deposits at Jezero crater preserve detailed records of ancient river systems that transported sediment into a standing lake. The fan-shaped deposit contains multiple episodes of river channel migration and avulsion. Grain size analysis reveals fluctuating discharge rates that suggest seasonal or longer-term climate variations. The delta stratigraphy shows alternating fine-grained and coarse-grained layers recording flood and drought cycles. Orbital imagery resolves individual sediment layers that accumulated over thousands of years. The preservation of delicate sedimentary structures indicates rapid burial that prevented destruction by later geological processes. These ancient lake systems provided stable aqueous environments that could support microbial ecosystems for extended periods. Atmospheric monitoring by multiple Mars missions tracks seasonal dust storm development and global circulation patterns. Regional dust storms originate in specific geographic locations during predictable seasonal periods. The 2018 Global Dust Storm provided detailed observations of how local storms expand to planet-wide events. Dust particle size distributions affect atmospheric heating and cooling rates that drive circulation patterns. Temperature measurements show how dust loading modifies the atmospheric thermal structure. These observations inform weather prediction models for future human missions that must operate safely during dust storm seasons. Mars exploration has revealed a planet with active atmospheric chemistry, seasonal cycles, and potentially ongoing geological processes. Yet even as we map the geology and chemistry of our planetary neighbor in unprecedented detail, the vast majority of matter and energy that shapes cosmic evolution remains completely invisible to our instruments. The dark universe deepens. This invisible cosmos operates according to physical laws that remain largely beyond our comprehension. Protons, neutrons, electrons, and all the atoms they form account for merely 5% of everything that exists in the universe. The remaining 95% consists of dark matter and dark energy, substances that emit no light, absorb no radiation, and interact with ordinary matter only through gravitational forces. This compositional breakdown means that everything humans have ever observed, measured, or touched represents a tiny fraction of cosmic reality. Dark matter outweighs ordinary matter by a ratio of roughly 5-1, while dark energy comprises approximately 70% of the universe's total energy density. Underground laboratories buried beneath miles of rock shield sensitive detectors from cosmic radiation that would otherwise overwhelm dark matter signals. The Xenon collaboration operates liquid xenon detectors in Italian mountain tunnels, monitoring for rare collisions between dark matter particles and xenon nuclei. These experiments achieve backgrounds so low that a single dark matter interaction would register as a significant detection. Cryogenic detectors cooled to temperatures near absolute zero measure tiny energy deposits from hypothetical dark matter collisions. Future experiments will employ even larger detection volumes and improved background rejection techniques. The Alpha Magnetic Spectrometer aboard the International Space Station analyzes high-energy particle spectra for evidence of dark matter decay products. Gravitational lensing reveals dark matter distribution by observing how massive galaxy clusters distort light from background galaxies. Multiple images of the same distant galaxy appear around massive lens systems, with image positions and magnifications encoding information about the lensing mass distribution. Weak lensing studies detect subtle shape distortions in millions of background galaxies to map dark matter across vast cosmic volumes. The Dark Energy Survey analyzed light from 26 million galaxies to create detailed dark matter maps showing cosmic web filaments connecting galaxy clusters across hundreds of millions of light years. The Euclid Space Telescope will extend weak lensing measurements to billions of galaxies, providing unprecedented precision in dark matter mapping. The Hubble constant controversy reveals fundamental tensions in our understanding of cosmic expansion and dark energy behavior. Local measurements using Type Ia supernovae and Cepheid variable stars indicate expansion rates of approximately 73 kilometers per second per megaparsec. Cosmic microwave background observations yield values near 67 kilometers per second per megaparsec when analyzed through standard cosmological models. This 10% discrepancy exceeds measurement uncertainties and suggests systematic errors or new physics. The James Webb Space Telescope has refined distance measurements to nearby galaxies, confirming the higher local expansion rate. The disagreement might indicate that dark energy properties change over cosmic time rather than remaining constant as assumed in standard models. The Dark Energy Spectroscopic Instrument has created the largest three-dimensional map of the universe, using data from nearly 15 million galaxies and quasars spanning 11 billion years of cosmic time. Recent findings suggest that dark energy, previously thought to be constant, may be evolving over time. This challenges the standard cosmological model and indicates that dark energy's impact could be weakening, potentially leading to changes in the universe's expansion in the distant future. These measurements track how cosmic structures have evolved and provide the most precise observations of dark energy's influence across cosmic history. Modified gravity theories attempt to explain galactic rotation curves and cosmic acceleration without invoking dark matter or dark energy. Modified Newtonian dynamics proposes that gravitational acceleration follows different laws at extremely low values characteristic of galaxy outskirts. These modifications successfully reproduce observed rotation curves in many spiral galaxies without requiring dark matter halos. However, most modified gravity models face significant challenges in simultaneously explaining galactic dynamics, cosmic microwave background observations, and Big Bang nucleosynthesis. Axion searches employ sensitive electromagnetic field detectors to capture hypothetical particles, converting into photons within strong magnetic fields. The Axion dark matter experiment uses superconducting magnets to create resonant cavities, where axions would produce detectable microwave signals. Laboratory searches probe specific axion mass, ranges through careful tuning of detector frequencies and magnetic field strengths. Stellar cooling observations constrain axion coupling strengths by requiring that axion emission not significantly alter stellar evolution timescales. Cosmic structure formation simulations require precise assumptions about dark matter particle properties to reproduce observed galaxy distributions. Cold dark matter models assume that dark matter particles moved non-relativistically during structure formation, allowing gravitational collapse on all scales. Self-interacting dark matter models introduce particle collisions that affect the density profiles of galactic halos. N-body simulations track billions of dark matter particles through cosmic evolution to predict galaxy formation timelines and clustering patterns. Galaxy surveys measure baryon acoustic oscillations, the imprint of sound waves from the early universe preserved in current galaxy clustering patterns. Redshift space distortions encode information about cosmic expansion and structure growth rates influenced by dark energy. Statistical analysis of galaxy clustering constrains cosmological parameters with unprecedented precision. Despite revolutionary advances in observational cosmology and particle physics, the fundamental nature of the universe's dominant components remains completely unknown. The vast datasets required to map this invisible cosmos and detect these elusive particles generate information at scales that exceed human analytical capabilities. Artificial intelligence transforms space science. Machine learning algorithms now process these astronomical datasets at computational speeds that dwarf human analytical capabilities. Modern sky surveys generate terabytes of information each night from automated telescope networks, with the Large Synoptic Survey Telescope capturing 15 terabytes of raw data during every observing session. Human astronomers cannot examine every image, spectrum, or data point collected by these instruments. Artificial intelligence systems operate continuously without fatigue, analyzing data streams in real time as telescopes collect observations. The Zwicky Transient Facility processes over 1 million alerts daily, identifying changes in brightness or position across the entire visible sky. These algorithms eliminate the bottleneck between data collection and scientific analysis that previously limited astronomical discovery rates. Pattern recognition systems automatically identify asteroids, variable stars, supernovae, and other transient phenomena from continuous monitoring programs. The Catalina Real-Time Transient Survey employs machine learning to distinguish genuine astronomical events from instrumental artifacts, cosmic ray hits, and atmospheric effects. These systems learn to recognize the characteristic signatures of different object types through training on millions of previously classified examples. Convolutional neural networks excel at identifying subtle patterns in astronomical images that human observers might miss entirely. The algorithms achieve detection rates exceeding 95% accuracy while processing thousands of images per hour. Automated classification systems now identify more new celestial objects in a single night than human astronomers discovered during entire decades of the 20th century. Galaxy classification represents one of artificial intelligence's most successful astronomical applications, with neural networks achieving accuracy rates that surpass trained human experts. The Galaxy Zoo project initially relied on citizen scientists to classify galaxy shapes from Hubble Space Telescope images. Machine learning algorithms trained on these human classifications now automatically categorize millions of galaxies by morphological type, star formation rate, and structural features. Deep learning networks identify spiral arms, galactic bars, merger signatures, and other complex features in galaxy images. These systems process galaxy surveys containing hundreds of millions of objects, creating statistical samples impossible to achieve through human classification. Automated analysis reveals rare galaxy types and unusual morphologies that occur too infrequently for human observers to notice during initial surveys. Exoplanet detection algorithms analyze photometric time series data to identify the characteristic brightness dips caused by planetary transits across stellar disks. The Kepler Space Telescope collected 4 years of continuous brightness measurements for over 150,000 stars. Machine learning algorithms sift through these light curves, distinguishing genuine planetary signals from stellar variability, instrumental noise, and systematic effects. Neural networks trained on confirmed exoplanet transits recognize the distinctive brightness decreases that indicate planetary passages. These systems identify transit candidates missed during initial human analysis of Kepler data. The algorithms achieve false positive rates below 1%, while detecting planets with radii as small as Earth orbiting Sun-like stars. Space weather prediction employs machine learning models that analyze solar magnetic field configurations, coronal mass ejection properties, and solar wind parameters to forecast geomagnetic storms. These algorithms process real-time data from solar observatories, automatically recognizing patterns associated with solar flare eruptions and coronal mass ejections. Neural networks trained on decades of solar activity data predict the arrival time and intensity of solar storms affecting Earth's magnetosphere. The Space Weather Prediction Center uses these models to provide advance warnings for satellite operators, power grid managers, and aviation authorities. Predictive algorithms analyze solar magnetic field images to identify active regions likely to produce major flares within 24 to 48 hours. Telescope scheduling algorithms optimize observation strategies by considering weather forecasts, target visibility windows, instrumental constraints, and scientific priorities. These systems automatically generate efficient observing sequences that maximize scientific productivity during available telescope time. Machine learning models predict optimal scheduling decisions based on historical weather patterns, target coordinates, and instrument configurations. The algorithms balance competing observational requests from multiple research programs while accommodating maintenance requirements and calibration procedures. Automated scheduling increases telescope efficiency by 15 to 20% compared to human-generated observation plans. Gravitational wave data analysis relies heavily on machine learning algorithms that identify merger signals buried within instrumental noise from laser interferometer detectors. The Laser Interferometer Gravitational Wave Observatory generates continuous data streams containing potential gravitational wave signatures from colliding black holes and neutron stars. Pattern matching algorithms compare observed data against theoretical waveform templates calculated from general relativity predictions. Machine learning systems filter out noise sources including seismic vibrations, thermal fluctuations, and laser frequency variations that mask genuine gravitational wave signals. Deep learning networks automatically characterize detected events, determining the masses, spins, and distance of merging compact objects. Spectroscopic analysis algorithms automatically determine stellar temperatures, chemical abundances, surface gravities, and rotation velocities from high-resolution spectra, containing thousands of absorption lines. These systems analyze spectra from millions of stars observed by large-scale surveys like the Apache Point Observatory Galactic Evolution Experiment. Machine learning models trained on synthetic stellar spectra achieve measurement precision comparable to expert human analysis. Neural networks identify rare stellar types, chemical peculiarities, and binary star systems through automated spectral classification. Automated analysis reveals galactic chemical evolution patterns, stellar population characteristics, and kinematic structures throughout the Milky Way galaxy. Multi-wavelength correlation algorithms combine observations from radio, infrared, optical, ultraviolet, X-ray, and gamma-ray telescopes to create comprehensive pictures of astronomical phenomena. Machine learning systems automatically identify the same celestial objects observed at different wavelengths, despite significant differences in appearance and position accuracy. These cross-matching algorithms handle systematic position errors, proper motion effects, and temporal variability that complicate multi-wavelength associations. Neural networks recognize correlations between emission properties across different wavelength ranges, revealing physical processes operating in stellar atmospheres, accretion disks, and galactic nuclei. Artificial intelligence has transformed astronomy from a discovery-limited field into a data-rich environment where computational analysis drives scientific breakthroughs. Yet the sophisticated algorithms and massive computing resources required for these advances represent only one aspect of the technological revolution reshaping space exploration. The democratization of space access through innovative engineering approaches has opened entirely new possibilities for astronomical research and discovery. Private space exploration accelerates discovery. Commercial rocket companies have fundamentally altered the economics and accessibility of space-based research through breakthrough engineering innovations. SpaceX's Falcon 9 rocket achieved the transformation that revolutionized commercial space access through successful recovery and reuse of its first-stage boosters. The company demonstrated that rocket stages could return to Earth under powered flight, landing vertically on autonomous drone ships or concrete pads. This engineering achievement reduced launch costs from over $100 million per mission to approximately $60 million for reused boosters. Blue Origin's New Shepard vehicle proved that suborbital flights could operate with airline-like reusability and safety margins. The B-3 engine burns liquid hydrogen and oxygen, producing only water vapor as exhaust while delivering 110,000 pounds of thrust. Rocket Lab's Electron booster uses electric turbopumps powered by lithium batteries, eliminating complex fuel-rich preburner cycles that plagued earlier rocket designs. These reusable systems have increased global launch frequency from fewer than 100 missions annually to over 180 orbital launches in 2023 alone. Planet Labs operates the largest constellation of Earth observation satellites, with over 200 active imaging spacecraft providing daily coverage of the entire planet's land surface. These CubeSats capture multispectral images at 3-meter resolution, enabling scientists to monitor deforestation, urban development, and agricultural changes in near real time. Capella Space deploys synthetic aperture radar satellites that penetrate clouds and operate during nighttime conditions, revealing surface changes invisible to optical instruments. Black Sky's constellation combines high-resolution imaging with artificial intelligence analysis to automatically detect ship movements, construction projects, and environmental changes. These commercial observation platforms generate datasets exceeding government satellite capabilities, while operating at fractions of traditional mission costs. Virgin Galactic has flown over 100 private individuals to the edge of space, creating opportunities for citizen scientists to conduct microgravity experiments during suborbital flights. These research programs include protein crystallization studies, fluid physics experiments, and atmospheric measurement projects designed by university researchers. Blue Origin's New Shepard missions carry automated research payloads alongside human passengers, conducting materials science experiments that require brief periods of weightlessness. The commercial crews perform simple experimental procedures during their 4-minute weightless periods, collecting data on plant growth, combustion behavior, and human physiological responses. Space tourism flights provide cost-effective access to microgravity conditions that previously required expensive orbital missions or parabolic aircraft flights. Axiom Space plans to construct the first commercial space station by attaching modules to the International Space Station before separating as an independent facility. The Axiom Station will provide laboratory space, manufacturing facilities, and residential quarters for extended orbital missions. These commercial platforms will host astronomical telescopes, materials processing equipment, and biological research laboratories operating in permanent microgravity environments. The stations enable long-duration experiments impossible during brief suborbital flights or limited space shuttle missions. Commercial crew vehicles from SpaceX and Boeing provide regular transportation to these facilities, reducing dependence on Russian Soyuz spacecraft. SpaceX's planned lunar missions include cargo deliveries to support NASA's Artemis program and private expeditions funded by commercial customers. The Starship HLS variant will transport astronauts from lunar orbit to the moon's surface using liquid methane and oxygen propulsion systems. Intuitive Machines operates robotic lunar landers that deliver scientific instruments and technology demonstrations to various locations across the lunar surface. Astrobotic's Peregrine lander carries NASA payloads alongside commercial cargo to study lunar soil composition and subsurface ice deposits. These private missions complement government programs while expanding the frequency and geographic diversity of lunar exploration activities. Thousands of small satellites now monitor cosmic phenomena including solar activity, magnetic field variations, and radio emissions from celestial sources. The European Space Agency's Swarm constellation uses 3 satellites to map Earth's magnetic field with unprecedented precision, revealing how solar-wind interactions affect our planet's magnetosphere. Commercial satellite operators integrate space, weather monitoring instruments into their communication and navigation satellite platforms. These distributed sensor networks provide continuous coverage of space environment conditions that affect satellite operations, power grids, and radio communications. Private investors fund next-generation space telescope development through companies like Relativity Space, which uses 3D printing technology to manufacture rocket components and satellite structures. The Terran R rocket will launch large space telescopes and interplanetary probes using methane-fueled engines produced through additive manufacturing processes. Firefly Aerospace develops small launch vehicles optimized for deploying CubeSat telescopes and scientific instruments to specialized orbits. Private funding accelerates telescope development timelines by eliminating lengthy government procurement processes and budget approval cycles. Universities partner with commercial space companies to access orbital research platforms and launch services at reduced costs compared to traditional government programs. Commercial rideshare programs allow small research satellites to reach orbit alongside primary payloads, dramatically reducing launch costs for academic institutions. Private companies offer turnkey satellite services including design, construction, launch, and operations support for university research programs. These partnerships enable smaller institutions to participate in space-based research that was previously available only to major universities with substantial government contracts. Competition between private space companies drives rapid innovation in propulsion systems, spacecraft design, manufacturing techniques, and mission operations procedures. SpaceX's success with reusable rockets prompted competitors to develop their own recovery and reuse technologies. Blue Origin's BE-4 engine uses oxygen-rich staged combustion cycles that provide higher performance than traditional rocket engines. The competitive environment encourages companies to develop breakthrough technologies that exceed government-specified requirements and performance standards. Private space exploration has evolved from entrepreneurial ventures into a thriving industry that provides essential services for scientific research and commercial applications. Yet the ultimate goal of human space exploration extends beyond Earth orbit to destinations that have remained untouched by human presence for over half a century. The Artemis era and lunar science renaissance. NASA's Artemis program represents the systematic return to lunar exploration through increasingly sophisticated missions designed for permanent human presence. The Space Launch System successfully completed its first uncrewed test flight on November 16, 2022, demonstrating that NASA's most powerful rocket could deliver the Orion spacecraft to lunar orbit and return it safely to Earth. The crewed Artemis II mission, scheduled for early 2026, will carry 4 astronauts around the Moon without landing, testing life support systems and spacecraft operations in the deep space environment. Artemis III represents the culmination of this preparation, with 2 astronauts planned to land near the lunar South Pole in mid-2027. These missions establish the foundation for permanent human presence through a series of increasingly complex operations extending through 2031 and beyond, incorporating advanced technologies including the Human Landing System, pressurized rovers, and surface habitats that will support extended lunar expeditions. The Lunar Gateway orbits the Moon as a solar-powered communication hub and scientific laboratory serving multiple research functions. The power and propulsion element provides electrical power and enables spacecraft to access any location on the lunar surface through ion propulsion systems. The Habitation and Logistics Outpost offers life support capabilities, command and control systems, and docking ports for visiting spacecraft. The Gateway's unique lunar orbit allows continuous communication with Earth while providing staging areas for surface operations. Astronomical instruments mounted on the Gateway will observe deep space without atmospheric interference or radio frequency pollution from Earth. European Space Agency contributions include habitat modules and refueling systems that extend the Gateway's operational capabilities, creating humanity's first permanent outpost beyond Earth orbit. Commercial lunar payload services missions deploy robotic landers across the lunar surface to scout resources and conduct scientific investigations. Astrobotic technology and intuitive machines operate these automated spacecraft under NASA contracts that reduce mission costs compared to traditional government programs. The landers carry instruments that analyze soil composition, measure subsurface ice deposits, and test equipment for future human missions. These robotic precursors map terrain features and identify hazards that could affect astronaut safety during surface operations. The missions target the lunar South Pole region, where permanently shadowed craters contain billions of tons of water ice. Automated drilling systems extract core samples from depths exceeding several meters below the surface, while solar arrays and nuclear power sources enable continuous operations during the 14-day lunar night. Ancient impact craters preserve 4 billion years of solar system bombardment history in their rock formations and shock metamorphic minerals. The Moon lacks atmospheric weathering and plate tectonics that destroy impact records on Earth, maintaining pristine examples of crater formation processes. Large impact basins like the South Polaican Basin expose deep crustal materials that reveal the Moon's internal structure and composition. Shocked minerals within impact breccias record the pressures and temperatures generated during asteroid and comet collisions. The lunar highlands preserve the oldest crustal rocks formed during the Moon's initial differentiation from a global magma ocean. Mare basalts fill impact basins with volcanic flows that erupted billions of years after the initial bombardment period, establishing chronological frameworks for understanding planetary evolution throughout the solar system. Lunar-based telescopes will exploit the Moon's stable platform and absence of atmospheric disturbances to achieve unprecedented astronomical precision. The far side of the Moon provides complete radio silence from Earth's interference, enabling sensitive radio astronomy observations impossible from terrestrial locations. Optical telescopes constructed from lunar materials could achieve apertures exceeding 100 meters in diameter under the Moon's low gravity conditions. Cryogenic cooling systems operating in permanently shadowed regions would eliminate thermal noise that limits infrared detector sensitivity. Automated construction systems would assemble these instruments without the launch mass constraints that limit Earth-based telescope sizes, while the Moon's slow rotation period provides stable pointing for extended observations of faint astronomical targets. Apollo samples and recent meteorite studies reveal complex organic compounds including amino acids, nucleotide bases, and polycyclic aromatic hydrocarbons embedded in lunar soils. These molecules arrived through impacts of carbonaceous asteroids and comets during the late heavy bombardment period approximately 4 billion years ago. The organic materials survived in the lunar environment due to low temperatures in permanently shadowed regions and protection from cosmic radiation within soil grains. Laboratory analysis of returned samples identifies specific molecular structures that could serve as precursors for biological systems. The preservation of organics on the airless moon provides insights into the delivery mechanisms that supplied Earth with the chemical ingredients necessary for life's emergence. International partnerships coordinate lunar exploration efforts among space agencies from the United States, Europe, Japan, Canada, and other participating nations. The Artemis Accords establish frameworks for peaceful cooperation, resource sharing, and scientific data exchange among partner countries. Japan contributes the pressurized lunar cruiser rover capable of supporting 2 astronauts for up to 30 days during extended traverses. European Space Agency modules provide life support systems and logistics capabilities for the Lunar Gateway Station. These collaborations distribute development costs while leveraging each nation's technological strengths and manufacturing capabilities, establishing precedents for future international missions throughout the solar system. Lunar geology samples and seismic measurements provide ground truth data for understanding planetary formation processes that operated during the solar system's earliest epochs. The moon's differentiated structure demonstrates how gravitational energy converted into heat during accretion, creating magma oceans that separated heavy and light materials. Impact crater density measurements calibrate bombardment rates that affected all inner solar system bodies during their early evolution. The moon's lack of a significant magnetic field provides insights into dynamo generation mechanisms operating within planetary cores. These investigations reveal fundamental processes that shape terrestrial planets throughout the galaxy, while establishing operational capabilities for exploring increasingly distant worlds, where even more extreme gravitational phenomena await detection through entirely different observational methods. Gravitational wave astronomy matures. The LIGO and Virgo detector networks now routinely capture these spacetime distortions, transforming Einstein's 1916 theoretical prediction into humanity's newest observational tool. Einstein predicted gravitational waves as ripples in spacetime itself, caused by accelerating masses that distort the fabric of the universe. These waves travel at the speed of light, carrying information about the most violent cosmic events across billions of light years. Unlike electromagnetic radiation, gravitational waves pass through matter without absorption or scattering, providing direct access to phenomena hidden behind dust clouds or occurring in environments too extreme for light to escape. The waves represent compressions and expansions of space itself, alternately stretching and squeezing distances between objects as they propagate outward from their sources. The Laser Interferometer Gravitational Wave Observatory operates 2 facilities in Louisiana and Washington state, each containing L-shaped vacuum chambers extending 4 kilometers in length. Laser beams travel between mirrors suspended at each arm's end, creating interference patterns sensitive to distance changes smaller than 1/10,000th the width of a proton. When gravitational waves pass through Earth, they cause minute alterations in these arm lengths that sophisticated photodetectors can measure. The Virgo detector in Italy employs similar principles with 3-kilometer arms, while the KAGRA facility in Japan operates underground to reduce seismic noise. Advanced LIGO achieved its first detection on September 14, 2015, recording gravitational waves from 2 black holes with masses 29 and 36 times our Sun, colliding 1.3 billion light-years away. Since then, The global network has detected over 90 merger events, establishing gravitational wave astronomy as routine observation. Multi-messenger astronomy combines gravitational wave detections with simultaneous observations across the electromagnetic spectrum, creating comprehensive pictures of cosmic catastrophes. The collision of two neutron stars on August 17, 2017, produced gravitational waves detected by LIGO and Virgo, followed by gamma-ray bursts observed by the Fermi Space Telescope within 2 seconds. Optical telescopes worldwide spotted the kilonova explosion in galaxy NGC 4993, while X-ray and radio observations tracked the expanding debris cloud over subsequent weeks. This coordinated campaign revealed how heavy elements like gold and platinum form during neutron-star mergers through rapid neutron capture processes. Such multi-messenger events occur approximately once per year, offering unprecedented insights into cosmic phenomena that gravitational waves or electromagnetic observations alone cannot fully characterize. Gravitational wave observations test Einstein's general relativity under conditions impossible to recreate in terrestrial laboratories. Black hole mergers involve gravitational fields billions of times stronger than those near Earth, with spacetime curvatures approaching theoretical maximums. The detected waveforms match general relativity predictions with extraordinary precision, confirming that massive objects falling into black holes follow trajectories calculated from Einstein's field equations. Binary black holes spiral inward exactly as predicted by gravitational wave energy loss, with orbital frequencies increasing according to theoretical formulas. These observations have confirmed that gravitational waves propagate at light speed, possess two polarization states, and carry energy away from their sources as Einstein predicted. Neutron-star collisions create conditions more extreme than those inside atomic nuclei, compressing matter to densities exceeding 100 trillion kilograms per cubic meter. When two neutron stars merge, their crusts shatter and nuclear matter mixes at temperatures reaching 100 billion degrees Celsius. The collision ejects neutron-rich material into space, where rapid neutron capture processes synthesize elements heavier than iron. Gold, platinum, uranium, and other rare elements form within seconds during these cosmic furnaces. The ejected material glows from radioactive decay, creating kilonova explosions visible across cosmological distances. Gravitational wave observations combined with optical spectroscopy reveal the total mass of heavy elements produced, typically equivalent to several Earth masses of gold. The Laser Interferometer Space Antenna will deploy 3 spacecraft in a triangular formation with arm lengths of 2.5 million kilometers, providing sensitivity to gravitational waves with frequencies between 0.1 MHz and 1 Hz. This space-based detector will observe supermassive black hole mergers throughout cosmic history, stellar mass objects spiraling into galactic center black holes, and potentially the gravitational wave background from the early universe. Einstein Telescope represents the next generation of ground-based detectors, employing underground facilities with 10-kilometer arms and cryogenic cooling to achieve 10 times greater sensitivity than current instruments. The confirmed detection catalog includes black holes ranging from 5 to 142 solar masses, revealing unexpected diversity in the compact object population. Binary black hole systems show mass ratios from nearly equal partners to extreme cases where one black hole significantly outweighs its companion. Spin measurements indicate that many black holes rotate rapidly, carrying angular momentum from their stellar progenitors. The merger rate averages approximately 1 event per cubic gigaparsec per year for stellar mass black holes, suggesting that the universe produces these systems continuously through massive star evolution. Gravitational wave astronomy has matured from experimental physics into an essential tool for understanding cosmic evolution. Yet each detection reveals the vast scales and energies operating throughout the universe that dwarf human comprehension and highlight the fundamental limits of our cosmic perspective, the frontiers we cannot yet cross. Beyond these detectable phenomena lies a universe that remains fundamentally inaccessible to human observation and understanding. Our most sophisticated telescopes peer 13.8 billion light-years into space, yet this represents only the observable universe bounded by the cosmic horizon, beyond which no information can reach us. The James Webb Space Telescope detects galaxies formed when the universe was merely 400 million years old, but we cannot observe what lies beyond this boundary. Light from more distant regions has not had sufficient time to travel to Earth since the Big Bang occurred. This fundamental limitation means that vast portions of the universe remain permanently hidden from direct observation. The cosmic microwave background radiation marks the furthest observable boundary, representing the moment when the universe became transparent to electromagnetic radiation. Beyond this wall lies the universe's true extent, which might stretch infinitely in all directions or curve back upon itself in ways our measurements cannot determine. The nature of time itself presents paradoxes that astronomical observations reveal, but cannot resolve. Einstein's relativity demonstrates that time flows differently under various gravitational conditions and reference frames. Near massive objects like black holes, time dilation effects become extreme, with seconds at the event horizon corresponding to years for distant observers. Yet we lack any framework for understanding whether time represents a fundamental property of reality or emerges from deeper underlying processes. Quantum mechanics suggests that time might not exist at the smallest scales, while cosmology requires time to explain the universe's evolution from initial conditions. The arrow of time appears connected to entropy increase and cosmic expansion, but the relationship between these phenomena remains mysterious. Space presents equally profound mysteries that transcend our current theoretical frameworks. General relativity describes spacetime as a dynamic fabric that curves in response to mass and energy. Yet this geometric interpretation leaves fundamental questions unanswered. Whether space consists of discrete units at the Planck scale or represents a continuous medium remains unknown. The vacuum of empty space appears to possess energy density and virtual particle fluctuations, but calculations of vacuum energy exceed observational limits by more than 120 orders of magnitude. This cosmological constant problem represents the worst theoretical prediction in physics history. String theory proposes additional spatial dimensions beyond the three we observe, but these extra dimensions remain completely inaccessible to experimental verification. The observable universe's boundary raises the possibility of parallel universes or alternate realities that exist beyond our detection capabilities. Cosmic inflation theory suggests that our observable region represents a tiny fraction of a vastly larger multiverse, containing countless bubble universes with different physical constants and laws. These parallel domains would remain forever unobservable due to the exponential expansion that separates them from our cosmic neighborhood. Quantum mechanics implies that reality branches into multiple parallel histories through wave function collapse, creating infinite versions of the universe corresponding to different measurement outcomes. These multiverse hypotheses remain scientifically untestable because they make no observable predictions that distinguish them from single universe models. The question of consciousness represents perhaps the deepest mystery confronting human understanding of the universe. We cannot define consciousness precisely enough to search for it systematically among other species on Earth, much less recognize alien forms of intelligence that might operate through completely different principles. Consciousness might emerge from specific arrangements of matter and energy, or it could represent a fundamental property of the universe like mass and charge. If consciousness permeates the universe, then intelligence might exist in forms we cannot imagine, potentially distributed through galactic structures, plasma phenomena, or quantum field fluctuations. Our anthropocentric perspective limits our ability to recognize intelligence that operates through radically different substrates or timescales. Interstellar travel remains beyond human technological capabilities due to fundamental physical and engineering limitations. The nearest star system lies over 4 light-years away, requiring spacecraft velocities approaching significant fractions of light speed to reach within human lifetimes. Accelerating massive objects to such velocities demands energy resources that exceed global production by factors of millions or billions. Chemical rockets cannot achieve the specific impulse needed for interstellar missions. Nuclear propulsion systems face unsolved problems with radiation shielding, fuel storage, and engine durability over decades-long journeys. Even robotic interstellar probes would require centuries to reach their destinations and additional years to transmit data back to Earth. Astronomical observation inherently studies the universe's past rather than its present state due to light's finite travel time. When we observe the Andromeda Galaxy, we see light that departed 2.5 million years ago when early human ancestors walked the African savanna. The most distant galaxies appear as they existed when the universe was young, showing conditions that vanished billions of years ago. This temporal delay means we can never observe cosmic events as they happen in real time. The universe continues evolving while we study ancient light, creating a fundamental disconnect between observed phenomena and current reality. Quantum effects operate on scales far too small for direct observation in cosmic structures, despite their fundamental importance for understanding reality. Individual quantum events influence macroscopic phenomena through complex emergent processes that obscure their underlying mechanisms. The quantum vacuum fluctuations that may have seeded cosmic structure formation during inflation remain unobservable due to their microscopic nature and ancient origin. Black hole information paradoxes arise from quantum mechanics applied to general relativity, yet we cannot observe quantum processes operating near event horizons. The universe's fundamental quantum nature remains hidden beneath layers of emergent classical behavior. Our terrestrial vantage point constrains cosmic understanding through atmospheric interference and geographic limitations that space-based observations only partially overcome. Earth's location in the galaxy's suburbs provides limited perspectives on galactic center phenomena and extragalactic structures. Our position in cosmic time means we observe the universe during a specific epoch that may not represent typical conditions throughout cosmic history. Each astronomical discovery reveals new questions that exceed the number of problems solved, demonstrating that the universe operates according to principles that continue to challenge our most sophisticated theoretical frameworks and observational capabilities. These limitations define the boundaries within which human cosmic exploration must operate. Our cosmic knowledge in 2025 represents 4 centuries of accumulated observation and measurement. We have cataloged over 5,600 worlds orbiting distant stars. The James Webb Space Telescope reveals galaxies from when the universe was young, yet this achievement illuminates how much remains unknown. Dark matter and dark energy comprise 95% of existence while staying completely mysterious. Each discovery creates new questions faster than we find answers. The universe proves stranger than our theories predicted. We live during humanity's golden age of space exploration. Revolutionary observations reshape our understanding annually. Our expanding knowledge reveals an increasingly complex cosmos that exceeds imagination.